Here we go, nerds. We are going to finish section 3.3 today. At long last, it's going to come to an end. Complex numbers.
I love that title card.
Yeah, that title card's pretty cool, huh? Daniel Quevedo?
Oh, I like the idea.
Yeah, he made this. Daniel Q. He made that for me. Isn't it awesome? This title card. Yeah, he made that for me. Anywho, what are we doing? Yeah, we're finishing section 3.3. We're going to start section 3.3, or the end of 3.3, I should say, by talking about complex conjugates and what that means. I would like to remind you what a conjugate is. So if you were to flip back 2 pages, 1, 2, jokes, 3, what the heck? I'm lost. Where is my stuff? Oh, my paper stuck together. I can count. It was 2 pages back, just like I said. This little box was part of our solving by factoring notes. And what this box shows us is the difference of 2 squares factors to a plus b times a minus b. And it specifically says these are conjugates. So if you have perfect square minus perfect square, you can factor that into a plus b times a minus b. Order of multiplication doesn't matter. But these are known as conjugates, where the only thing that changes is the symbol in between the 2 structures. This is pretty cool because if you do it backwards, if you multiply conjugates, what you'll always get is perfect square minus perfect square. And that is extremely important to us. Come back to today's notes. Talking about complex conjugates. Yesterday we talked about the standard form of a complex number is a plus bi. The conjugate of a plus bi is a minus bi. The reason why this is significant is because complex solutions to quadratics will always come in conjugate pairs. Complex answers to any polynomials will always come in conjugate pairs. We call them complex conjugates. That means if 2 plus 3i is one of your solutions, it guarantees 2 minus 3i is another solution. If 4i is a solution, it guarantees negative 4i is also a solution. If 1 minus 5i is a solution, guarantees 1 plus 5i is a solution. I hope you guys can see where this is going. No, meaning you could follow the pattern. Okay, so they always come in conjugate pairs. The reason why is actually because of something that we haven't reviewed yet. We will, but for now, I'm just going to sneak it into the notes. You don't need to write it. We're going to have a whole lesson on it. Boop! Ye olde quadratic formula. You learned the quadratic formula in Algebra 1. Notice, please, that it has a plus or minus in it. You saw a video 2 days ago, quick little 5-minute video titled Imaginary Numbers Are Real. And remember what they did in the videos, they showed you that x squared plus 1 doesn't ever cross the x-axis. So its solutions are imaginary. If you attempt to use the quadratic formula when your quadratic never touches the x-axis, what will happen, and don't worry, this will end up in our notes eventually, what will happen is that b squared minus 4ac would end up being negative. And the square root of a negative number is always imaginary. Notice it's number plus that imaginary, number minus that imaginary. And that is why they will always come in conjugate pairs like this, where all you do is change the symbol in between the 2 things. It's because of the quadratic formula. Cool beans? Cool beans. Great. So for these examples, what we're going to do is we're going to first find our complex conjugate, and then once we have it, we will find the product of our 2 complex conjugates. So that'll give us an opportunity to review what we did yesterday, which was multiply complex numbers. Somebody in the room, I'm sure, has noticed there's a new letter on the paper somewhere. Z. Can we find imaginary or complex numbers on our x-axis? No, they do not exist on the x-axis. So when we've been solving quadratics, every time we've solved one, our answer was x equals something or other, right? But if your answers have I in them, that means they don't exist on the x-axis. So it doesn't really make sense to say x equals that complex number. Z, lowercase z, is the letter that mathematicians chose to use to represent complex answers. That's all that means. Don't worry, it won't affect you in any way except for just know that anytime I'm going to write answer equals and the answer is complex, I'm going to write z equals instead of x equals. Because that's what mathematicians use. They use z. And so that we don't get confused and have two different things that say z equals, typically it'll say something like z sub 1 and z sub 2, meaning the first z and the second z. Doesn't matter which one you call the first one, which one you call the second one. That's not important. What is important is that they have separate names. That way you don't think they're equal to each other. Okay? What we have here then is the complex number z sub 1, 2 plus 5i. Its complex conjugate, since this is in standard form, is very, very simple. You just change that plus sign to a minus sign. Our complex conjugate then, z sub 2, is 2 minus 5i. Don't overthink it. Your job is just to change the symbol in front of the imaginary component. That's your job. Yes, Riley, that's it, because if we come back 2 pages like I said earlier, you'll notice the only difference between these two things is one has a plus in front of b and the other has a minus in front of b. These just happen to have an I after the B. Cool. Let us find the product of these two complex numbers. We are going to have to go through our distribution process, which I'm sure some of you like to call FOIL. We'll do 2 times 2. We'll do 2 times negative 5i. We'll do 5i times 2. And we'll do 5i times negative 5i. Uh-oh. Is my orange pen dying right here on camera? No, my orange pen's doing fantastic. Why isn't it working?
You have to hit it.
I'm gonna hit something, that's for sure. All right, let's see. Let's see. Me trying the bottom of my shoe. Maybe the roller ball froze up. Come on now. Yeah, they're ballpoint pins. They have rollers on the end of them.
Just hit it. Lick it.
Lick it?
Yeah.
I just rubbed it on the bottom of my shoe. Why would I lick it? What's wrong with you people?
When you dab it on your tongue, it reactivates the ball. It makes it easier to move.
So what you're saying is that the ball is dry. Okay, well, I tell you what. I'm not licking a shoe pin, so I'll just switch colors. Anyway, that almost worked. I just won't use orange anymore for this lesson. There. All right, 2 times 2 is 4. 2 times negative 5i is negative 10i. 5i times 2 is positive 10i. And 5i times negative 5i is negative 25i squared. And something really neat happens every time you multiply two complex conjugates. The middle terms will always be exactly the same number, but will have opposite symbols, so the middle terms will cancel every time. That is going to give us 4 minus 25i squared. But if you can recall to the previous lessons, what does I squared equal? Negative 1. So what we have here is 4 minus 25 times negative 1. That is 4 plus 25. Look at that. I multiplied two complex numbers, and the result was a real number. Isn't that neato mosquito? But it can be. He says it can't be. It definitely can, because check this out. The terms in the middle that would have had just I on them canceled each other out. Think about it like this. What's I times I? I squared, which is negative 1, right? So clearly there's a way to multiply complex numbers to get real numbers. If you multiply complex conjugates, you will always get a real solution or a real result every single time, which is pretty cool. And it's very useful to us. Our new Z1 is not in standard form. So we cannot find its complex conjugate until we get it into standard form. First, the square root of negative 4 is 2i. This is still not in standard form. A plus bi is standard form, meaning the I has to come last. So 2i can't be in the front of this thing. 2i needs to be in the back. But the 3 is negative. So we have negative 3 plus 2i. And now we can find our complex conjugate. The complex conjugate of negative 3 plus 2i will be Negative 3 minus 2i. You just change the symbol of the imaginary component. That's all you do. Now, I don't want to go through this foiling process. I want to skip this step right here, and we can do that very, very simply. Let me show you how. It's going to require me to flip back 2 pages again and remind you what happens when you multiply conjugates. When you multiply conjugates, you get a difference of 2 squares. So you square the front term, you square the back term, and you put a minus sign in between, which is exactly what happened on this line right here. I squared the 2, I squared 5i, I put a minus sign in between. So we didn't have to show this. Why did I do it? Because I wanted you to see why the middle stuff cancels out. But we could skip this line right here and go directly to this. Square the front, square the back, put a minus sign in between. Multiplying conjugates will always get you the difference of 2 squares. Square the front, square the back, put a minus sign in between. Negative 3 quantity squared is 9. Then now minus. What part? Negative 3 times negative 3 being 9? Okay, so we're going to go back 2 pages like I said a moment ago. And I'm going to show you, if you're multiplying conjugates, you square the front number, you square the back number, you put a minus sign in between. So square the negative 3, square the 2i, put a minus sign in between. It's going to give us 4i squared. But because I squared is negative 1, this setup, well, this actually 4i squared is actually negative 4. So what it says is 9 minus negative 4, which is 9 plus 4. So 13. Yes, it is a whole lot of math. I know it's shocking being in a math classroom and all, but sometimes there is a lot of math. One more time. When you multiply complex conjugates, you will always get a real result. I squared the negative 3, I squared the 2i, I put a minus sign in between. Yes? I had 9 minus negative 4 equals 13. Because 4i squared is negative 4. Because I squared is negative 1. Nine plus 4, yes. And that's how I got 13. Yep. And not only can we use complex conjugate products to get real numbers, we can also use this same conjugate trick to get rational numbers if we multiply irrational conjugates.
So what's that z to the z thing?
There is no z to the z anywhere.
Or z with the z on it?
There is no z with a z under it. That's z sub 2. That's why I cross my z's. Yeah, I always cross my z's. Have you not noticed that yet this year? See how all of my z's have a cross in the middle of them? Okay. So if you don't see a cross in the middle of it, you know it's not a z. That's unfortunate. Maybe you should move closer to the board. Anyway, I'm not sure I want you in the room, Hunter. But my point is, I always put a cross in the middle of my z's. So that way you know they're z's and not 2's. Always. It's also why I cross my 7's. That way they don't look like 1's. Because I know my handwriting is not very good. But no, this is z sub 2. That's just the other complex numbers, all I'm saying. Not the first one, but the second one. So anyway, this trick with irrational numbers can also be used to rationalize things. If you multiply irrational conjugates, you will always get a rational result. No more roots will be in the number. So that's pretty cool. And it's useful to us. How? For the one operation that you haven't seen yet with complex numbers. You've seen adding, you've seen subtracting, you've seen multiplying. Everybody's favorite operation, Division. And not only will we be dividing complex numbers, I'm also sneaking division of irrational numbers in these notes as well. Because why not? Oh no! Pieces of my orange pen just went flying when I did that. Where'd they go? I found them. Nobody freak out. Calm down. I found them. All right. Here we go. I'm not even actually dividing complex numbers here. This is a complex number. It just simply isn't in standard form. It is our duty to get it into standard form. The problem is there are more rules about the bottoms of fractions than you know. So this year we talked about how the bottom of a fraction can equal 0, right? It also cannot have any imaginary numbers in the denominator. So if you have an imaginary number in the denominator, you need a way of getting rid of this complex number. Hey, wait a minute. I could have sworn we just learned a way to make it so that there aren't complex numbers using multiplication. All we have to do is multiply by the complex conjugate on the top and bottom. The complex conjugate of 1 minus 4i is 1 plus 4i. On the top, in the numerators, you would have to distribute the 1. Of course, distributing a 1 is not going to change anything on top. So this is going to give me 1 plus 4i in my numerator, but on the bottom, I have the product of complex conjugates. Boom, just like that. I'm just multiplying the top and bottom by the complex conjugate. The reason why we're using the complex conjugate is because I can't have this I in the denominator, but I know for a fact from the last two examples that if I multiply these two complex conjugates, my denominator will be a real number.
Oh, I thought you were just adding 4i.
Nope, it's multiplication. Boop. So there you go. You know how when you have to find common denominator for adding and subtracting fractions, how you multiply to the top and the bottom? It's the same setup. We're multiplying to the top and the bottom to the exact same number to make sure that we haven't actually changed the fraction, we've changed the way it looks. But this red thing equals 1, so we haven't actually changed it. In the denominator, again, you don't need to go through the following process if you know that the product of conjugates is always going to get you the difference of two squares. Square the front, square the back, put a minus sign in between. So my denominator is 1 minus 16i squared. But since I squared is negative 1, it'll be 1 plus 16 because it's actually 1 minus negative 16. That will give us 1 plus 4i over 17. We're still not finished, because this is not in a plus bi format. So it is still not in standard form. The way you get it into standard form is to split it into two fractions. 1 over 17 plus 4 over 17 with an I behind it. Now it says 1 plus bi. So is it incorrect to have this I on top of this fraction next to this 4? No, that's not incorrect. That's fine. It's just that you'll never see it written that way. It'll always have the I off of the fraction, almost like it's a variable. It's not a variable, but that's what it'll always look like. And just to show you, grab my graphing calculator. Oh, cleared my RAM. Okay. So let's see. Stack fraction, 1 over 1 minus 4i is 1 over 17 plus 4 over 17i. There you go.
And you can't leave it proper like that?
No, sir. It must be written like that. I know. But there's a reason why. You won't learn that reason this year, but you will next year in the next course. Mia, I heard you say you don't understand something, something, something.
Oh, well, I just was like, confused, like, how is it not a variable?
Because I has a numeric value, square root of negative 1. Okay. But it looks like a variable, doesn't it? Yep. It just can't take on, it's not an unknown, it's a undescribable. I think that's a better way of saying it. We can't describe it in our normal numbers. Next, Remember how I told you early in the year that there are no rules about the top of a fraction?
Yeah.
That's still true. There are no rules about the top of the fraction. Nobody cares what's up there. But you can't have an imaginary number in the bottom of the fraction. That means this complex number 2 minus 4i is a big fat no-no. In order to make it go away, you're going to have to multiply the top and bottom by the complex conjugate of 2 minus 4i, which is 2 plus 4i. In the numerator, there is no way to avoid it. We are going to have to FOIL. Yay! 2 plus 3i times 2 plus 4i on the bottom. 2 minus 4i times 2 plus 4i. At least we don't have to FOIL in the numerator and the denominator, right? We only have to do it once on top. Because on bottom, we're multiplying conjugates. Square the front, square the back. Put a minus sign in between. Square the front, square the back, put a minus sign in between. Ooh, in the numerator though, we have 2 times 2, 4, 2 times 4i, 8i, 3i times 2, 6i, 3i times 4i, 12i squared. But 12i squared is negative 12. And, well, I'll clean up the denominator in just a second. Let's see, this numerator is going to give me 4 and negative 12. That's negative 8. And 8i plus 6i gets me 14i. I have 2 squared, which is 4, minus 16i squared, which is just actually going to be plus 16 because 16i squared equals negative 16. That will give us negative 8 plus 14i over, I wrote 12, but it was supposed to be 16. My apologies. There we go. 4 minus negative 16, 4 plus 16, 20. You will need to separate into 2 fractions and reduce your 2 fractions. Negative 8 over 20 plus 14 over 20i, and then reduce. If you divide the top and bottom of this by 4, you'll get negative 2/5. And for 14 and 20, you can divide them both by 2 and get 7 over 10. I, like that. Yay, we did it. Oh, okay, hold on. David?
I have a question. Where did you get negative 8 from?
Where did the 4 and the negative 12. I combined them to get negative 8.
Oh, okay.
It's 4 plus negative 12, which is negative 8. Yes, I squared is negative 1.
Yeah, right there.
Yeah.
So then how is negative 1 times negative 16 negative 16?
It's not. I didn't cross out the negative sign. 4 minus negative 16, which is 4 plus. Yeah, if you wanted to say that this was positive 16, you could and just say 4 plus 16.
Okay, so you just wrote 2 like minus.
Here's why. Here's why. A lot of times students will forget that this symbol is a piece of this number. And they'll say, oh, that's positive 16. And then they'll do 4 minus 16. And I'm trying to avoid that mistake where the students think it had to always be a minus by saying, well, what if we just looked at the number itself and saw that it was negative 16 and then say 4 minus that? And Joey, you had a hand up, but then it went down.
Must have been answered.
Okay. Let's check out this last one. No imaginary numbers.
Why is there so much space?
Because it was the last example and the paper I was done.
Oh, okay. It's not gonna
No, it doesn't take that long. It's no more work than the previous ones. So we have an irrational denominator. The next rule about the bottom of a fraction bar is,
Next rule.
yeah, the bottom, can't equal 0. We just talked about how the denominator can't have imaginaries in it. The next rule is denominators cannot have irrational numbers in them.
How many are there?
Well, that's 3 so far.
Oh, can tell me one.
No, that was only one you knew about. The good news is we get rid of irrational numbers the same way we get rid of complex numbers. You multiply by the conjugate. The conjugate of 3 minus root 5 is 3 plus root 5. There's so many voices right now. It's crazy. I don't want to use blue. I already used blue. Let's do green. Let's do green. I have 2, and I have a 3 plus root 5. You are welcome to distribute that if you'd like to, but you don't need to. It doesn't make a difference. Square the front. Square the back. Put a minus sign in between. And this square and this square root cancel each other. I hear people saying in the back. Yep. So what is that going to get me? Do you guys want to distribute the 2 on top? It doesn't matter. Okay. If we distribute the 2, it'll give me 6 plus 2 root 5. I forgot to put my exponent of 2 there. My apologies. I forgot to put the exponent there. Down here I have 3 squared, which is 9, minus the root and the square have canceled each other. 9 minus 5, which is 4. Which 2? This 2, you want to know where it went? I distributed it. All you need to do now is get it into standard form, which looks just like standard form for complex numbers. Write it as 2 fractions. And reduce the fractions independent of one another. If you divide the top and bottom of this one by 2, you get 3 over 2. If you divide the top and bottom of this one by 2, you get root 5 over 2. And that's it. See, Joey didn't need a lot of extra space. I just wanted to make sure that, I just wanted to finish the notes without doing redundant stuff. And that's going to do it. Unless there's any questions about it. Are there questions about it before I stop the video?
No, thank you.
No? Okay, then it stopped.